Any general questions, problems, anything? Right. I think March 2nd or whatever it was. Date is on the Dropbox, I believe. I think I changed them both. Okay, we were talking integrated rate laws, and again, it's a slightly different view of the kinetics. You really can sort of tell what type of problem it is just from the data I have. I don't, in some sense, even need the words, right? If I see that, I'm thinking method of initial rates, because experimentally what I have is the measured rate for a bunch of different starting concentrations, right? That looks similar but different than an integrated rate law problem where time is expressly a parameter. And so I really have one beaker measured at different times, right? And again, just based on the data set, there are tells as to what type of problem I'm talking about, right? And of course, I could graph it and use it to find the rate law, but as I was saying at the end of class on Wednesday, right, that is awkward, right? Because I'm looking for the best fit straight line among a bunch of lines that all might be reasonably well fit, or if you're sloppy with the experiment, all might be horribly bad fits, right? And so I'm not sure how definitive I feel about something that's just the best of a bad lot, right? To that end, I think it's far more common to use initial rates as a means of establishing the rate law, right? That said, my rate law and integrated rate law, of course, go hand in hand. One's the integration of the other. It really just depends on whether I'm concerned with the time evolution of the reaction, right? Or whether I'm really completely changing the mixture in the beaker, in which case all I really care about is the rate law. And so, again, I may not care to measure the time dependence of the reaction to get the rate law, but if I already found the rate law using the initial rates, the integrated rate law should apply. And so in that vein, right, if I have this reaction and it's first order in chlorine and first order overall, right, since I have the orders, I know both the rate law and the integrated rate law, right? This problem itself, right, is really, again, an integrated rate law because the tell is that it's asking me about time, right? Rate laws are great for calculating the rate at a specific instant when I have a known concentration, right, and I have a K at a known temperature, right? On the other hand, rate laws directly tell me nothing about time. On the other hand, the integrated rate law does expressly tell me about time, right? And so this is an integrated rate law problem. And I know what the integrated rate law is because I know what the rate law is. All right. And so it's first order in chlorine and first order overall. And so I know both the rate law and the integrated rate law, right? It's first order in chlorine and first order overall, which means the hydrogen doesn't matter, right? That makes the rate law simply some rate constant times the chlorine to the first power. And again, as soon as I have the rate law, the integrated rate law is automatic. No need to integrate it again. I did it once. All first order rate laws, right, have a similar, nearly identical integrated rate law. The only thing that's different is what the chemical species is I'm talking about, right? And again, the integrated rate law is the direct integration of the rate law. So the only chemical species that works in the integrated rate law is the chlorine. If you don't care about chlorine, and you might not, the product here is HCl. A lot of times you might care about the product, right? Even if you care about HCl, the integrated rate law cannot calculate directly the HCl, right? Because it came from the integrated rate law, and the integrated rate law doesn't know about HCl or the regular rate law, right? Chlorine here, it has to be chlorine there, whether I care about it or not. Right. You can write that one of two ways. They're equivalent. And of course, either one of those could be used depending on what I'm trying to calculate, right? But both of them depend on knowing the rate constant, right? In this case, right, I would need to know the rate constant. This is technically probably the initial rate, or initial concentration, but it's, at the very least, it's chlorine at a specific point in time, right? In this case, I need to know K, and usually I need to know this, right? And what it tells me is something slightly different. This will just tell me what the rate is at that instant. This will tell me how much chlorine is left at a specific time. But in both cases, I need to know how much I'm starting with, right? And I also need to know the rate constant, right? If I take a moment to actually read the rest of the words in the problem, since I mostly just looked at time and the first order part of it so far, right? It doesn't actually give me the rate constant. What it does tell me is what the initial rate was when I mixed 2 molar hydrogen and 2 molar chlorine at 298 kelvins, right? And then it asks me the rate after 10 minutes and how much product I made after 10 minutes, right? So again, as in most problems that are at all algebraic in nature, right, there's the thing I know and the thing I don't know, right? It may be a little tricky here in that the thing it asks me for, I cannot directly calculate, right? There's no way for me to calculate directly the rate after 10 minutes. There's no way for me to calculate directly the HCl at any time because the rate law depends on chlorine, not HCl, and therefore the integrated rate law also depends on chlorine, not HCl. On the other hand, everything has to be related, right? And so if I look at what I actually know, I have a target time, right? At the moment, that's not very useful, right? I mean, I could put 10 minutes over here, but I don't know this, right? And so finding anything 10 minutes later is impossible until I have the rate constant. On the other hand, right, I do have an initial chlorine concentration, and I do know the rate, right, when that chlorine concentration is in effect. So in fact, I could use and will use the rate law to calculate the rate constant, right? Right. I always refer to it as the unfortunately named rate constant because it's not constant. However, it is constant for a reaction as long as the temperature doesn't change. So if I stay at 298 kelvins, it's the same K. Right. And so there's my initial rate. There's my initial chlorine concentration. It's first order, right? A little subtraction gives me the actual rate constant, right? That does operationalize my integrated rate law, right? As long as I know the initial concentration, which I did, and as long as I know the rate constant, which I now do, I can find the remaining chlorine concentration at any time. Right. Again, it doesn't actually ask me for the chlorine concentration, right? It asks me for the rate. I have no equation for rate that depends on time. It asks me for the HCl. I have no equation that tells me anything directly about HCl, but the HCl came from here, right? And I only make HCl if the chlorine reacts, right? So based on stoichiometry, right, if I know how much chlorine is left, I should know how much HCl I made. And that is what the integrated rate law tells me, how much chlorine is left at any time, right? And the other thing I do know, right, is the rate law itself, right? So even though, again, I cannot calculate the rate at 10 minutes, if I know what the chlorine concentration is at 10 minutes, the rate is always directly proportional on the chlorine. Right. And so in both cases, the questions I'm trying to address, right, are indirectly answered. And so pick your favorite time. In this case, it's 10 minutes. Again, as always, units, 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 by which I mean, of course, they must cancel. Since my rate constant was in reciprocal seconds, my time is going to have to be in seconds or the units don't cancel. Ten minutes is 600 seconds. All right, the initial concentration of chlorine is 2 molar. I've just got a number on the right-hand side. I've got a natural log on the left-hand side. The anti-function for the natural log is e to the x. So if I just take e to both sides, the natural log disappears on the left, and I end up with e to the minus 1.152, which of course is just a number on the right-hand side. And a little cross multiplication tells me that there should only be 0.632 molar chlorine left after 10 minutes. If you want to know after 30 minutes, change the time. If you want to know after 10 seconds, change the time. But that's what the integrated rate law tells me always, is how much, right, of one reactant is left after a given amount of time. Let's know. Be a little careful here. All right. Again, it asked me about HCl. Stoichiometry tells me I get 2 HCl's for every chlorine. Right. But there are always, and this becomes increasingly important in 10 minutes when we change to equilibrium, there are really always 3 amounts of anything in a reaction. Right? There are 3 amounts of hydrogen in this reaction at all times. There are 3 amounts of chlorine in this reaction at all times. There are 3 amounts of HCl in this reaction at all times. None of them, first of all, are stoichiometry. I do not have 2 moles of HCl and 1 mole of chlorine. All right. I have whatever I put in the beaker. So initially, right, I had 2 molar hydrogen. Right. Initially, I had 2 molar chlorine. Initially, I have 0 molar HCl. Then there's always the amount that reacted. Initially, that's 0, right? But 10 minutes later, it's not 0, right? And so the 3 amounts that are always present in any reaction are really the initial amounts, right? The final amounts, and the amount that actually reacted, which is the difference between the initial and final amounts. I bring this up because, right, if I want the amount of HCl, I can't get it from the amount of chlorine left. Right, I just discovered that there's 0.632 molar chlorine left. Stoichiometry never applies to what I have.
right? I mean, I could have started with 2 molar hydrogen and 20 molars of chlorine, right? There is not a one-to-one relationship between what I throw in the beaker. There's not necessarily a one-to-one relationship between what's left over, right? If I started with 2 and 20, the reaction's over. I have no hydrogen and 18 chlorines. There's no relationship. Stoichiometry only applies to the amount of stuff that actually reacted. In a strange sort of way, stoichiometry really applies to the stuff you don't have anymore. All right, I can start with whatever I want. What I end up with is going to depend on what I start with. The only thing the reaction really tells me is every time one hydrogen reacts, and therefore no longer is hydrogen, one chlorine reacts and is also no longer chlorine, and one H or two HCl's are made, right? And those actually exist, right? And so if I want the rate, the only thing I know to give me the rate is the rate law. And since the chlorine is now down to 0.632, I have a new rate. Right? This is why reactions slow down in time. You're constantly losing reactants. And so K should still be the same as long as the temperature didn't change. All right, and so the rate is just K times well, however much chlorine is left. All right, the HCl I can get from the chlorine, but not technically the 632. All right, it's not how much chlorine I have, it's how much chlorine reacted. Right, so if I look at my initial amounts, I changed it to mole. You could do it in molarity, but some people get confused by that. I had a 5 liter flask with 2 moles per liter. There were 10 moles initially. There are 3.16 moles left. Again, technically, stoichiometry does not apply to either one of those numbers. Right. The stoichiometry reaction applies to the amount that actually reacted, which is the difference between what I started with and what I ended with. So if I started with 10 moles of chlorine and I ended up with 3.16 moles, all right, 6.84 moles of chlorine reacted. That, in the context of the stoichiometry of the reaction, tells me how much HCl I made. Right? Because I do get 2 moles of HCl for every 1 mole of chlorine that reacted. If I wanted to spend more time with bigger units, right? It's really not moles of chlorine, it's specifically moles of chlorine that reacted. Yes, no, maybe.
When you're asked for the rate at a specific time, can you just differentiate the integrated rate law and search for rate at a given time?
Well, if you differ, yes and no. I mean, if you differentiate, the question for those of you home is if you needed the rate at a specific time, could you differentiate the integrated rate law? You could, except that doesn't really tell you anything specific that I didn't already know. If I differentiate my integrated rate law, I'm going to get this.
You can solve the integrated rate law. What's the expression?
Well, yeah, but I mean, where is my integrated rate law? If I, the only thing I'm expressly integrating is I know this and I know this, which is still just going to give me this with those two numbers plugged in. Right? I mean, I love a little calculus, but right, I already know all I need to know about the differential of the integrated rate law because I got the integrated rate law from integrating that. Right. Yes, no. Other questions? The owl homework does mention half-life. It's worth mentioning. It's not a huge issue most of the time. It does pop up in nuclear chemistry, which with a little luck we'll talk about in May for like a day. But half-life is just really a different way of specifying the rate constant. All right. And it really isn't terribly useful, right, except in the context of a first order equation. Because a funny thing happens in a first order equation, right? If I rearrange that slightly, right, where I've got the log over the log, right? In fact, the initial concentration cancels if I look at the fraction that remains, right? And theoretically, you could do this with any remaining amount, right? There's a 90% life, right? See how long it takes for 90% to be left, right? There's a 10% life. See how long it takes for 10% to be left, right? For historical reasons, again, mostly related, I think, to radioactivity, people frequently refer to the half-life, which is technically the time it takes, right, for half of whatever you start with to react. And again, in the context of a first order rate law, the amount of time it takes for half to react is independent of how much you started with, right? Because it cancels, right? And so, in fact, for integrated first order rate law, essentially the log of a half, which again was really half of what I started with, but what I started with canceled, right, is always minus KT, which would be the time it took for half to react. And so that's why I say really half-life in the context, I'm going to keep saying it, of a first order reaction is always just an indirect way of giving me the rate constant, right? The half-life just differs from the rate constant by that log of a half, which is what the 0.693 is, right? Right? In the context of a first order rate law, that's kind of interesting, right? In the sense that what it means is no matter what you start with, it always takes you the same amount of time to get to half. That also includes while the reaction is happening, right? If I start with 1 molar, the amount of time it takes me to get to a half is exactly the same amount of time as it takes me to get to half of a half, which is now a quarter. All right. And once I'm at a quarter, it takes me exactly the same amount of time to get to half of that, which is an eighth. And so you have very fixed time intervals during which you're always losing half, no matter what you started with, right? Start with 1 billion pounds. After a half-life is passed, you have 500 million. Start with 1 gram. After that same amount of time, you have 0.5 gram. It's in some sense a mathematical oddity. I only bring it up because historically, this sometimes gets referenced, almost always just for first order reactions, right? Because the problem with non-first order reactions, I need space here somewhere, right? If it's a non-first order reaction, you don't get the same cancellation, right? By which I mean, right, if I play the same game with a second order reaction, right, half-life would be where A of t is 1/2 A0. right? If I do that, I can play the same basic game, but what I have over here, right, in the end is 1 over A0 equals K times the half-life, right? This is 2 over A0 minus 1 over A0. All right. In that case, the half-life is not independent of my starting concentration. And so I don't have this very constant time period where I keep losing half of my stuff. All right. They call that a divorce. It's a good joke. You should laugh. Right? If I do the same thing with the 0th order, I have the same problem. I can define a half-life, but my half-life ends up depending on what I started with. It's only, again, sort of a mathematical quirk that if I have a first order, right, kinetics, the integrated rate law results in a half-life that is independent of what I started with. I would guess nobody would care at all about half-lives except for nuclear reactions, because it turns out all nuclear decays are first order. Right. And so they will specify that the half-life of uranium is 10,000 years. Right. And it's useful to know that for uranium, because that means every 10,000 years you use half no matter how much you have, because it's first order kinetics. If it had second order kinetics, I couldn't so easily specify it. Right. It would be 10,000 years times the initial concentration if it was second order. Right. But just so you know, you'll get some owl practice, and we will look at it again in that day or two where we talk about nuclear reactions at the very end of the semester.
What day are
Questions
these
on that?
what day are these upcoming sprints
Right.
due?
Other than that, that's kinetics in a nutshell. All right. The rate law, again, most generically defined, will tell me the rate no matter what's in the beaker at a split second in time, right? And at a specific temperature. The integrated rate law will tell me how much of a single one of the reactants, the reactant from the rate law, is left at any point in time, right? You know, whether you think of those as one thing or two, I leave to you. After all, the integrated rate law is just the integral of the rate law. So again, it's really all about the rate law. Okay. Questions, problems?
I have a question, Professor.
Okay. Shifting gears to what is really the biggest single topic of Chem 2, which is equilibrium. It also starts the period of this class that I think of as my attempt to undo all the lies you've been told. Some of them possibly even by me. And of course, by lies, I mean oversimplifications, right? And there's a lot of them that pop up in this section, and some of the ones from high school are incredibly impossible, virtually, to, I've entered the Joe zone. It's it's incredibly impossible. I don't even know what that means. It's incredibly impossible to knock out of your head some of the preconceptions you might have from high school, which can be problematic here, because it's not that they're wrong, even though I'm going to keep referring to them as lies, right? But they're oversimplifications, and we want a more general sense of the equilibrium, not the very specific simplified version that you might have seen earlier. And really, one of the lies that I'm trying to undo was the lie I told you in the fall, which is that reactions, whoops, proceed from left to right until you run out of something, right? In a word or two, right? This is a limiting reagent problem. And up till now, that's how we've essentially looked at all reactions. Right? In fact, mere moments ago, I referenced the hydrogen and HCl reaction as though it went to completion and I was out of chlorine. Right? In fact, most reactions are not limiting reagent problems because of a reason that goes back to what, again, I always refer to as the most important graph in all of general chemistry, which we just saw in the context of my rate constant in the Arrhenius model, where the activation energy was the key. It still sort of is, right? The hard part in any reaction is getting over the hump. Right? But here's the thing, right, about my journey over the barrier to go from reactants to products. It doesn't look that different backwards. Right? I literally just flipped the whole diagram around. I mean, there's a slight difference, right? This reaction is endothermic, right? Whereas this was exothermic, because delta H is now opposite in sign, right? Because instead of ending up at a lower energy state, as I did here, I ended up at a higher energy state. My activation energy is slightly different, right? Because this direction, my barrier is the activation energy of the other direction plus the delta H, right? Or if you prefer, right, this activation energy is the activation energy of the reverse process minus the delta H, right? And so it's a little harder to go one way than the other because the barrier is a little higher. But here's the thing, for most reactions, the delta H is smaller than the activation energy, often by a lot, right? And so even though technically, if I'm going this way, I have both of those energies I need to overcome, right? The activation energy is the biggest component. So my hill is only slightly higher here. All right. So as a result, most reactions tend to go both ways. Which means I don't really have a limiting reactant type problem where everything just keeps going one way until you run out of something. Because while it's going one way, it's also going the other way. All right. And if I were to, for a second, run out of something, the reverse reaction would start remaking it. Right. And so in general, reactions can go both ways. We'll talk later in the semester about some types of reactions that don't. It's not 100% true that no reaction goes as a limiting reactant problem, right? But to treat that as the normal condition is actually really, I would argue, the opposite, right? Most reactions actually proceed in an equilibrium fashion because it's not that much harder to go one way than the other. And limiting reactant problems are that simplified version of what happens in the rare instance where it can only go in one way and not both ways. Right. Okay. That really changes the way I would approach an actual chemistry problem. All right, because up till now, if I had an actual good old chemical reaction, like the one we just had with the hydrogen and the chlorine, right, I've been treating it as though it proceeds naturally to a point where I run out of the limiting reactant. Right. And so if I'm asked what happens when I mix these two things together, the answer is frequently it keeps reacting until I have no chlorine left, at which point I have 10 moles of HCl, right? And I've told you exactly, right, how the reaction ends, right? That is now not true. Instead of proceeding to where I run out of something, right, I proceed to a point of balance between the reactants and the products. Right. Now, this point of balance is really not static, right? Which also fundamentally changes the way I think about the reactions. In a limiting reactant world, right, my reaction proceeds till I'm out of something and then everything stops. Right? In an equilibrium world, I proceed to this point of balance, but my point of balance is really more a question of balancing two things that are happening simultaneously and continue to happen. Right? And so equilibria are often referred to as dynamic equilibria, meaning that I reach this point of balance where it looks like things aren't changing, but that's because there's two things changing in an equal and opposite fashion, right? From a kinetic standpoint, right, my point of balance is the point at which the forward rate and the reverse rate balance each other, right? And so if I think of my reverse rate as being the undoing of the products, right, and my forward rate as being the making of the product, right, these would initially be at different rates, right? If you think about initially, typically initially, I don't have any of this, right? And so initially, the reverse rate is 0. I can't unmake C until I make C, right? But if I start making C, right, in terms of my good old rate laws, right, for my reverse reaction, the rate's going to depend on C to some power, whereas the forward rate's going to depend on, you know, one or both. But like any reaction, I'm changing the amounts as the reaction occurs, right? If I make products, I have more C and less A. If I run the reverse reaction, I have less C and more A. And so my rates aren't constant, right? And so you get eventually to the point where the forward and reverse rates are equal, right, by balancing the concentrations, so that ultimately my rate of creation of the product here, C, is the same as my rate of destruction. Right? That might occur when I'm mostly out of A, and so I have to mostly do the reverse reaction. Right? It might happen when I have very little product, because the reverse reaction is normally faster than the forward reaction, right? And you can sort of see this in action in what I often refer to as my sit-stand reaction, right? In a smaller class or a class where all, well, you're home now, you know, your video's off. While you're at home, you know, stand up and sit down, right? But my reaction is literally you standing or you sitting, right? And so I could write a rate law for the forward reaction, and I could write a rate law for the reverse reaction. I will make one up, right? It really doesn't matter whether the one I make up was correct or not, right? I'm going to make up an order. I'm going to make up a rate constant. If you want to play it at home, do the exact same thing with a different rate constant and a different order of the reaction, and you'll find out that the same thing basically happens, although the balance point is different. And so just for simplicity, I'm going to make it first order, right? And so my forward reaction has a rate that depends to the first power, on my only reactant, which is the number of people standing. Okay. And I'm going to need a rate constant, and I'll make one up in a minute, right? I'm going to do the same thing for the reverse reaction. Again, they don't have to be the same. One could be first order, one could be third order. They could be first orders both, second orders both. What's ultimately going to happen when I do this won't really change. It's just the point of balance that will change. Right. And so just so I have actual numbers and can do the math, I'm going to make up a rate constant. The rate constants will be different. Right? Because again, if you think about it in terms of my diagram, my activation energy, think Arrhenius, right? My activation energy is different for the forward and the reverse reaction because of the delta H. So there is no reason why I would expect the rate constants to be the same. But again, for simplicity of math, I pick a very simple 1/2 for the forward reaction and 1/4 for the reverse reaction. Right. Okay, and I will do something that in the context of a limiting reactant problem would seem totally illogical, right? I'm going to start with all of you sitting, which is actually the product, right? If this was a limiting reactant problem, this would be a trick question on the test, right? Here's my reaction. I have 180 grams of product. Right? How much product do I have when the reaction ends? Answer 180 grams. Because in a limiting reactant problem, I can only go in one direction. But since I can go in both directions, it really doesn't matter if I start with 100% products or 100% reactants. Doesn't matter if I start 50 and 50, right? I could have started with 90 of you standing and 90 of you sitting. Ultimately, the same thing happens, right? And so I'm going to take my first time interval and look at the rate law, right? My rate is half the standers in the forward reaction, and it's 1/4 of the sitters, right? And as you can see, because I have a different number of standers and sitters and I have a different rate constant, I have a different rate for the forward and the reverse reaction, right? The number of sitters is 180. 1/4 of 180 is 45, right? Which is what this number is. And so in that first time interval, 45 of my sitters stand, right? I have 0 standers. So in fact, I cannot do initially the forward reaction. I don't have the reactant, right? And so in that first time interval, 45 people who were sitting stand and 0 people who were standing sit. And so I have a net change of 45 people, right? I now have 45 people standing, and that leaves me with 135 people sitting, right? That changes both rates, right? Because I have a different concentration, a different number of sitters and a different number of standers. It's still 1/4 the number of sitters, right? And it's half the number of standers, but the number's different. So now my forward reaction in my second time interval is half the number of standers. I'm going to round here, right? So it's half of my 45, which is 23. And my reverse reaction is still 1/4 of the number of sitters, but I now only have 135 sitters, right? And so in my second time interval, 39 of you who are sitting stand, but 23 of you who are standing sit. Right? Which gives you a net change of 16. Right? And so I now have 16 more people standing than previously, and I have 16 fewer people sitting, or 61 and 119, right? And the same thing happens in the third interval, right? Half the standers sit, 1/4 of the sitters stand, right? You can see now what's happening because the number of standards have grown, that rate keeps getting higher. Because the number of sitters has been decreasing, that rate keeps getting smaller. Right. And in that third time interval, right, Half of 61, again, rounding is 31 people. A quarter of 119, again, rounding is 30 people. That's a net difference of 1. Right. Which gets me to 60 people standing and 120 people sitting. Right. At that point, half of 60 is 30 and a quarter of 120 is 30. Right. From that moment onward, the number of people sitting is changing at exactly the same rate as the number of people standing. Right, I've got 30 going from sit to stand and 30 going from stand to sit, which is a net change of 0. Right, and so from that moment forward, there are always 120 people sitting and 60 people standing, but they're not always the same people. Right, in every time frame, 30 of those 60 people sit down and 30 of those 120 people stand up. Right, so for the rest of all eternity, this will be the Gen Chem version of hell. You just stay there, standing and sitting, standing and sitting, standing and sitting. Right. And so that's what I mean by a dynamic equilibrium. The reaction really never stops, but it has reached my equilibrium, right? Point of balance, call it, right? Where I always have 60 people standing and I always have 120 people sitting. And so there's no net change in the amount of things in my beaker, or in this case, in my classroom, right? But there is constantly reaction chemistry going on in both directions. All right. And so now my goal, when confronted quantitatively with a chemical reaction, right, is not to see what runs out. It's to find what that point of balance is. In this case, my point of balance is twice as many sitters as standards. And spoiler alert, if you were to start this with 240 people with the same kinetics, you would end up with 160 people sitting and 80 people standing, right? Because of the rate constants I chose, there's always going to be twice as many sitters as standards. If I change the rate constants, that ratio would change, right? But for any reaction, there is always this point of balance where my rate going forward is the same as my rate going in reverse, and things are just happening in both directions in a way that cancels any net change. And so my goal, equilibrium-wise, is to find that position for my reaction, because that is now my endpoint for the reaction, right? It's no longer see what runs out first, right? It's see what my position of balance is between the products and reactants. And we will define that on Monday, which is almost like a Friday because Tuesday's a recovery day, for what that's worth. Questions or problems? Did we get an answer to the question in the chat? Honestly, I could not see the chat for a while there because it blinks out, but
I have a quick question.
I mean, Quinn's answer is mostly the issue with the radioactive decays. The other way to look at it is you only have one reactant in a radioactive decay. There's nothing for it to collide with or anything else.
Can you hear us or no? Okay.
No, I cannot hear you. Can you hear me? It's weird. Hang on. Somebody say something.
Test, test, test.
Can't hear anything. It's very strange.